Pokémon Legends ZA dropped on October 16th, 2025, and it's a much different Pokémon game than the old classics. It has new catching and battling mechanics, plus a super cool online competitive mode. However, the only issue is that the campaign, like many recent Pokémon games, has become pretty overbearing, with hours of unskippable dialogue and repetitive quests. So, while I was working through the campaign, I set up a few basic macros using an open source library and an Xbox remote, just so that I could mash through dialogue or catch a bunch of shinies overnight. All this being towards the goal of playing competitive mode with a bunch of shiny Pokemon as fast as possible. And all of that cutscene downtime gave me some room to think. AlphaGo proved long ago that AI can outplay us at almost any game, which usually leaves me feeling like gaming's a waste of time. But then self-driving came to mind. The AI takes the dull stretches and hands control back the moment you want it. And that was it. Let it do the boring quests, grind the levels, farm the resources, and collect the Pokemon I want to use. Then, drop me into the save right at the part I actually want to play. Only problem though, by the time I'd formalized this idea, I'd nearly finished the game. Nothing really left to hand off. But then I hit the competitive mode and realized the Z to A climb itself gave me a clean, gamified benchmark. And with a clear finish line in mind, suddenly this wasn't a vague wouldn't it be cool, but rather a well-scoped challenge. But the climb itself is just a test. What I actually want is to build an infrastructure underneath it. A stack that you can point at any Switch game and have it learn to play. Pokemon Legends ZA is just how we find out if it works. So, here's the goal. Given any Switch game, we'll be able to train an AI to master it. The metric for whether we've pulled it off is if we reach the top of the ladder in Pokemon Legends ZA. Additionally, in the spirit of self-driving, we'll also build in an autopilot mode such that we can play the Nintendo Switch with our final AI, just like Tesla's FSD. The way the competitive mode works is completely different from the classic turn-based formula. Instead, you get a 4-player free-for-all in real time, 3 Pokemon each, 3 substitutions per cycle, and the points needed to rank up come from knocking out other Pokemon. Our model will have to learn how to search for targets and use attacks in order to win points that will move us up this ladder. Let's outline a few rules for the climb. There won't be any helping allowed. I won't let myself step in and help the AI mid-match. It plays the games, it takes the losses, and it'll earn the wins. Fine-tuning during the climb is fair game. The AI is allowed to keep learning as it plays. Let's get into it. As mentioned, we'll be making this all work with the Nintendo Switch. The video comes through an HDMI USB-C capture card. The actions stream from our computer to the Switch over Bluetooth. Since we're the ones sending them, we save each action as we send it, pair with the frame it lines up with. The video gets saved as MKV or MP4, and our actions will be in a Parquet. As done commas work, we'll use the same Stable Diffusion autoencoder for making latents to feed to our models. This dataset is what we'll use to train our models for the rest of the video. The most common place to begin is with how children do it. Copy what you see. In the technical literature, this is called imitation learning, or behavior cloning. You record hours of expert gameplay, every frame paired with every input, and train a model to reproduce the mapping. It's commonly done for targeted tasks in robotics, and it's the obvious first thing to try here. My first pass of data collection was a grab bag. Me wandering the maps, occasional battles, and general gameplay. The idea was that more variety meant a more well-rounded model. As it turned out, this was a bit of wishful thinking. I built a Roomba. The model picks up the controls fine. It can move, it can interact, but with no clear focus, it just wanders and ends up finding a corner to live in. The real issue is that it can't recover. Expert players don't record footage of getting unstuck because expert players don't get stuck. All in all, not exactly the Pokemon champion I was hoping for. So I narrowed the data, more footage of escaping corners, and more focus on finding opposing Pokemon, engaging, and attacking. And almost immediately, we get our first knockout. Okay, it did calm mind up. And ice beamed again. Didn't it? Oh, it got a kill! Let's go! This model is a good starting point, but it's still not very efficient at searching and targeting. The issue comes down to the competitive mode in Legends ZA taking place across 3 different maps, each with its own textures, its own boundaries, and its own weird geometry. And also, while it's better, the corner problem hasn't fully gone away. It'll get a knockout, then run straight to a corner and live there. To figure out what to do about that, we look at how the self-driving industry has handled the same kind of problem. Enter reinforcement learning. Reinforcement learning is about letting the AI play the game itself, and we'll tell it whether it's doing good or bad just based on the outcomes. Enemy Pokemon targeting and attacking gets a reward, while getting stuck in a corner gets a penalty. We can even build off the work so far, using the behavior cloning model as the starting policy and refining it with reinforcement learning. But reinforcement learning needs a place to play. The AI has to actually attempt all those matches somewhere, and the real Switch isn't going to cut it. Each match takes real time, and you can't run them in parallel on a console. So we look at how self-driving has solved the same problem. The classic answer is a simulator. Tesla, the whole industry has been training their models in physics-based driving simulators for a while. You train your policy in the sim for free, then deploy to the real car. We could do the same for Legends ZA. Just rebuild the game in code and let the AI grind there. And we really could, but I don't want to. That's a pretty big project on its own, and the sim still wouldn't match the real game. But then there's Google's Genie. You give it a starting frame or a text prompt, and it generates an entire playable game. You can press buttons, and the model invents what happens next, frame by frame. That's a world model, a neural network that's watched enough of something to learn its physics, rules, and visual logic well enough that it can simulate their experience from the inside. No engine, no hand-coded rules, just a model dreaming up plausible next frames. This is where self-driving has been heading to. Kama's recent work uses a world model in place of a hand-coded simulator. The thesis is that a model can learn the dynamics of the world end-to-end rather than introducing hand-coded rules. This really nerds me, so let's make one for our Pokemon game. The core formula driving our world model simulator is something called rectified flow. The intuition is to treat the next frame as some distance away from the current frame and train a model to predict the velocity needed to get there. This is just like one of the first equations you learn in physics. Distance equals position plus velocity times time. There's a lot more depth here, the math, the training tricks, but I'll point you at my repo and the Dreama and Kama papers if you want to go deep. And after many experiments, an overnight training run, here's ours running live. One important note about how we're playing it. We're starting from real seed frames and actual screenshots, deliberately chosen near the situations we care about. If the AI gets stuck in a corner lot, we seed from a corner. And if it's not targeting during a battle, we seed from a battle. This is partly principled and partly pragmatic. It's principled because we want to train near the failure modes behavior cloning was struggling with, but there's no point in generating millions of frames of empty meadow. It's pragmatic because with two 3090s and a limited dataset, our world model's quality drops off the further it generates from a real frame. Anchoring on real seeds keeps things coherent for long enough to be useful. Now that we have a way to train the model, it's time to use it. We take the behavior clone model from earlier and fine-tune it with reinforcement learning inside the world model, and almost immediately, the behavior shifts. Where the behavior cloning version would just dead sprint into geometry and get wedged, the reinforcement learning version starts being deliberate. It hesitates near walls, it backs out of bad positions. This one's actually pretty fun to watch. Now all that's left to do is to let it climb to rank A. Here's a quick aside on how we actually extracted those rewards and penalty signals. Reinforcement learning needs a reward signal, and unlike a regular game engine where we can ask if we got a point or not, in our world model, there's no such engine to ask. There's just generated pixels, so we have to read the pixels. The Legends ZA UI is consistent. There's health bars, position indicators, and a mini-map. But there's one piece of UI that makes this work especially well. When something that looks like a Pokemon is in frame, and you press the lock-on button, a battle UI pops up. We reward the AI for hunting that state for hunting opponents and attacking while locked on. The clever part, this single reward solves two problems at once. It teaches the AI to fight, and it pulls it away from corners, because corners don't have Pokemon in them. Here's a short list of other rewards. We penalize how long the AI goes before targeting. We penalize the position similarity across recent frames to discourage standing still, and we also penalize looking straight up or down so it doesn't get lost staring at the sky. The framework is general. We add new reward signals by taking screenshots in our world model and using them to detect if the current frame the AI is at is similar to any of them. We use computer vision for this. For example, we can tell if the battle UI is present with edge detection because the outline is always the same. It's a hack, but it's the kind of hack that works. UI artifacts are the most stable, predictable part of any game's visuals. Exactly what we need when we're reading reward signals out of a generative model that might wobble in the rest of the scene. One thing I tried, but didn't stick with, was having the world model also predict actions and use those signals directly. So, sort of a more robust behavior clone. But what I noticed was that predictions tended to degrade the original model's backbone instead of helping. It's an idea that with more data and compute, I'd try next, perhaps with a focus on committing more heavily to future anchoring, as done in the Kama AI work. Once we got the model to a certain level of quality, I felt okay leaving the AI to play by itself. This was done just by detecting when the game ends and spamming A until the next game starts. The model is working well enough even that when I left and came back to it a few hours later, it was actually winning the game I walked in on. Dude, this thing's kicking ass. It's first place right now. Damn. And it keeps going, all the way up to rank A. In total, it took about 10 hours, a bit more than twice as long as it took me in a previous season. The repo has all the setup instructions if you want to do the climb with my model. If you train your own or run a different Pokemon team and get better results, drop a comment. This project took months, and here's a few things I do differently or just do more of when I pick it back up. First, the world model is the bottleneck here. With more data and more compute, a higher quality world model would let me do something I couldn't pull off this time. Having the world model itself predict actions and use those predictions to shape the reward signal alongside the computer vision-based rewards. Secondly, I would collect more data. The single biggest force multiplier in this whole project would have been having more gameplay footage. And there's a clean way to get it that I didn't pursue, an inverse dynamics model trained for extracting action frame data from YouTube videos. I actually started working on this, but put a pin in it when my early reinforcement learning agents started showing promising results. Both of these are on the list for next time. Thanks for watching. The full code for the world model, the behavior cloning pipeline, the reinforcement learning harness, the whole stack is on my GitHub. Fork it, point it at a different game, see what happens. I went into this thinking it wouldn't take that long, and as is tradition, it took about 3 times as long as I expected, which honestly reminds me of a clip I saw early on in the project. It's Kama's machine learning lead, Yasin, fielding questions after a presentation.
Leo said, I feel like building the simulator is not that hard. Trust me, Leo. Leo, we do things not because they're easy, but because we thought they were easy.